Hey, good afternoon, everybody. Welcome to today's webinar. My name is Maureen Gribble, and I work with UE Systems. And today we're kicking off a little webinar series that we're doing in conjunction with our Leading Reliability event. And so for those of you that aren't aware, the Leading Reliability brand has been around for several years now, but we really kind of took it off when it took off when COVID hit, and we used this as a great platform for these four companies, Iridicio and RDI Technologies and Fluke Reliability, and of course UE Systems, for us to be able to continue to share information and still be able to engage with folks, throughout the pandemic. We did some virtual conferences, and then in this past August, we were actually able to do an in-person conference, which went really well, and it was great to be back in person with folks. We have another in-person conference coming up May 10th through the 12th back in Clearwater Beach, Florida. So we hope you'll save the dates for that. Should be a great event. But in the meantime, we plan to do some of these webinars throughout the year. And so what we decided was to kick off this year with a little kind of back to the basics webinar series. So today is the first one, and of course we've got Jeff Hay from RDI Technologies, who's going to be talking about vibration. It's just physics. So this should be a great presentation today. Then we've got another one on Thursday. Skylar Horn with Iridicio is going to be presenting on shifting your mindset and just kind of preparing yourself for how to embrace change and how to move change forward. So again, a great topic to kick off the year with. And then we'll round things out with UE Systems next week. I believe it's next Thursday, where Adrian Messer is going to be talking about kind of an ultrasound 101. So all the different ways that you can utilize ultrasound at your facility, and hopefully give you guys some new ideas and applications that you might not have thought of. So hopefully you all enjoy this series, whether you're able to attend one or all of them. We will be recording all of the sessions, and we will make those recordings available. We have a LinkedIn, Leading Reliability LinkedIn group that you can follow. So we'll put that information there with the links and so forth. And of course, you can reach out to any of us as well if you want to track those down. We do welcome questions today, so we'll try and make it as interactive as we can with being virtual, of course, but there's a little Q&A box, so you can just type your questions into that. I'll be keeping an eye on those as Jeff is doing his presentation. So if there's anything that we need to kind of pause and get some clarification from Jeff on, we'll do so at that time. Otherwise, we'll of course do some Q&A at the end, and any questions we don't get to, we'll be sure the RDI Technology team gets those questions so they can follow up afterwards. And of course, just always like to remind, we are doing this live. So if we have any technical or audio issues, we will jump on fixing those as quickly as we can. If you hear any dogs barking, et cetera, but hopefully it should be smooth sailing. We're kind of old hats at this. So with that, I am going to turn the screen over here to Jeff, and Jeff will let you take it away.
Okay, thanks, Maureen. I am going to share my screen. Hopefully you can see my screen there, Maureen?
I see it, and it looks great.
Okay, great, thanks. Okay, so as Maureen mentioned, I'm going to be talking about the title of the talk's vibration. It's just physics, and appreciate that introduction, Maureen. And as she mentioned, the leading reliability. We've been doing this for a couple years now, and really enjoyed doing it because it's allowed us to stay connected. So I was at the Clearwater event in August, really good time, and looking forward to being there again this year, and hopefully we'll be able to have more of you be able to attend that. So going back to the talk, so today's talk, again, it's called vibration. It's just physics. So this is a vibration talk, but not necessarily a vibration talk. So I put vibration in quotations. I'll kind of just leave that as is, and I think you'll understand really what I mean once we get in this. We will be talking about vibration, just not necessarily in the typical sense that most of us are used to in this industry. As Maureen also mentioned, feel free to ask questions along the way, or in the the Q&A along the way, and then we'll get all those kind of together, and happy to answer any towards the end. I always like getting questions. So again, my name is Jeff Hay, CEO of RDI Technologies. My background is in an applied optical physics, so I started as an astronomer, but quickly sort of worked my way out of that field, really just going where the research kind of led me, and where we developed some technology at the university that was very good at detecting motion and characterizing that motion. And that laid the groundwork for developing what would later become motion amplification. That was originally done for Department of Defense and DHS. They were interested in sort of satellite-based surveillance, as well as looking at bridges and critical infrastructure. So you can imagine, being able to see very small movement from far away has lots of applications, not just necessarily motion amplification. But which is what we do at RDI. But and then I left to work with an industry, and then started RDI really to get the technology into people's hands so they could use it. Okay, so I started as an astronomer, so that's true. I did. I thought that I would be looking at one point in time, be looking at stars, through a telescope, or really astronomers don't really look at stars. That's a kind of a secret. I don't know if you don't know that. Very few astronomers actually look through an eyepiece these days. It's all done. Sometimes it's even done remotely. You're not even on site, or you're not even in the room with the telescope, but it's really done with a camera. And I would argue that looking at something far away, like you see on the left, and looking at a motor and a pump, maybe on the right, are way more connected than you think. And there's a lot that connects us, and the title of the talk some of that gives it away, but there's a lot more that connects us. I mean, in one case, you're looking at a galaxy light years away, and all you can do is use a camera to determine properties of it. And then in another case, you might be using a camera, like with motion amplification, to look at a motor. But again, you can't go and touch it. Everything that you have to discern from it is all gathered from the camera. So one happens to be light years away, one happens to be just a few meters away. But it's the same kind of problem set. It's the same kind of idea. So making that connection, I'm going to put this out, and I'm going to just kind of, you can feel free to, if you want to type in the Q&A or whatever, what you think this is. But I would look at this, and I would just propose, what do we think that is, right? You just kind of look at it, and you see some peaks, and those who are in the vibration industry may say, okay, well, are those units on the left-hand side, are those in inches? So that it's ranging from 0 to 1.6 mils of motion, and are those hertz, on the bottom, that tell me, like what is the amplitude of vibration at each frequency? Well, it actually turns out that is a peridogram, which actually determines the variation of a star in its light, so intensity. So that's power and frequency, but as a unit of 1/days. So again, something very similar to what we're used to seeing, but in a very different branch of physics, or in a very different area of expertise. Let me show you another one. So if you just look at that and you say, hey, what is that, right? What does that look like? Well, if you try to connect it back to maybe our industry in industrial machinery with vibration, you may say, well, that could be mode shapes, right? That's a first mode, a second bending mode, a third bending mode, maybe on a cantilever beam, right? The blue one is the first mode. But what that actually turns out to be are eigenstates for a quantum mechanical system. So again, just sort of connecting different areas, something that we're used to seeing, sort of a representation, shapes, and these patterns with other areas of science and physics. because really, with machinery vibrations, we're in, I would say mechanical, the mechanical side of physics. It's just one branch of physics. Okay, so the question is, what do machine vibrations, gravity, light, quantum, and quantum mechanics all have in common? So there might be more than one thing that connects these, but really for the purpose of this presentation, what is it that all of those things have in common? Well, it turns out they are all governed by the same wave mechanics, right? It's really waves that connect them. Waves are used throughout physics to describe lots of different things. And all those things, from quantum mechanics to the machine's vibration, wave mechanics can explain a lot of what we understand about those systems. So let's kind of take a look at that. And let's start with something very basic. F equals ma. This is probably maybe next to E equals mc squared. This might be one of the, at least in the top 3 physics equations or popular physics equations out there, right? So F equals ma. What does that say? Well, it says the force of something, the force that's being applied to something is equal to the mass times the acceleration, right? So increase the mass or you increase the acceleration, you have more force, right? So they're equal to each other. If you want to get fancy and write that in a different way, you can write it like this. And what that says is F equals ma, but the difference is the A has been replaced with the second derivative of position, which is just dx dt, or the second derivative. So really what that says is that it's the rate of change of the rate of change of x, or the rate of change of velocity, or the rate of change, the second rate of change of position. So you can write it that way. And then there's another equation, less popular, but also well known, is F equals negative kx. So this one also has a name, Hooke's law, right? And that just says that the force, like you think of like a spring or something like that, the force is equal to the negative, and then you've got the spring constant there, k, or the system constant, and then x. In other words, the more you displace it, the more force there is, but in the opposite direction of the way you displace it. So that makes sense. Like you take a rubber band or you take a spring, you stretch it one way, you stretch it to the right, and if you let go, it moves to the left. It's pulling to the left. The force is going in the opposite direction. So that's for a harmonic system. So we have 2 equations that describes a harmonic system, something that goes back and forth, right? And that's the restoring force is what essentially makes it kind of go back and forth, right? It overshoots, overshoots each time, goes back towards equilibrium as a restoring force. So we have 2 equations now, both equal to F, right? And now if 2 things are both equal to F, we're allowed to put them together and say they're equal to each other, right? F equals ma is equal to ma is equal to F, and negative kx is equal to F. So that means ma is equal to negative kx. Now, if we write it in that fancy way with the derivative there, we have mass times acceleration is equal to negative kx, but with the derivatives, and that is a differential equation, right? So that's they're not, some are easier to solve. This one's not too difficult to solve in terms of in the grand scheme of things with differential equations, but it has a really well-known solution. Most people don't actually do the solving; they already know the solution. Somebody's already worked it out for them, and we know the solution to that. In other words, if we want to solve for x, right? If we want to solve for x in this, turns out the solution to that equation is x is equal to cosine of omega t. And we might recognize this, a cosine function. That is a periodic function, something that goes back and forth. It varies over time. It goes up and down, right? So in other words, what it says is when you have F equals ma and negative kx with this restoring force, you get a periodic function as the solution. So in other words, it's a wave. The solution to this equation is a wave, right? And so let's look at that. So here we go, and we can see sort of like a spring. We talked about that, right? Moving up and down. But if you were to trace that kind of over time, you would describe a cosine or a sine function, right? You would have this wave that moved over time. So let's look at acceleration, velocity, and displacement, right? We've talked about those, F equals ma, and we saw for x the displacement. Let's look at that, and I'm going to use a visualization tool here. And so if you haven't seen these, there's a website, and you can see it up here, PHET. If you Google search PHET, it is done by the University of Colorado. So there was a Nobel Prize winner a few years ago that, when, I'm not sure if you're aware, but if you win the Nobel Prize, you get $1 million, right? And I always feel like it's the only way for physicists to become millionaires is you got to win the Nobel Prize, right? Because you get the $1 million that way. And because you're probably not going to do it in research otherwise. And so so when this guy won the Nobel Prize, he used a lot of his Nobel Prize money to sink it back into physics education. And so he developed these sort of tutorials that show it. So show different concepts very easily. You can do anything from quantum mechanics to looking at vibrations of atoms and molecules and things like that. So I would encourage you, if you're kind of curious, to check those out. And so that's PHET. Just Google search PHET physics simulations, and you'll see that. Okay, so I just want to do a real quick introduction here to this, and this is how easy it is. We've got a spring here, and we can just turn it on and off, and we can make it slow, right, so that you can watch it, right? And then we can put it in terms of vectors, and we can change the spring constant to large or small, right? So let's do that. Here we go. So we got it here. And then I just want to show you the velocity and the acceleration. So notice they're out of phase with one another. Those in vibration know that occurs, right? There's a lead and lag with position, acceleration, and velocity. But you can actually see that, right? And then you can actually see position here. So you can see where the difference, so you've got the green line, green arrow being displacement. So I just wanted to kind of show you this periodic motion here, and kind of show you, the relationship between, the mass, acceleration, velocity, displacement. And I encourage you again to check this out. But this is periodic motion, right? You can see that as over time it goes up and down, there's a restoring force to bring it back, right? As soon as it displaces one direction, the force builds up and pulls it back. And then as soon as it displaces that opposite direction, the force builds up and pulls it back. Okay. So let's have another way to look at periodic motion. So let's say that you have a periodic system and something that's going to go periodic, but you kind of put a constraint on it. You put a constraint that says, hey, you got to stay within these bounds. Like this spring can go back and forth, but there's a constraint on it to say it can only go so far, or some other system, like for example, somebody going up and down a hill, right? That would be periodic, right? We'll just drop that skater there, and she's going to go up and down, right? We don't have any friction in this, so it's a perfect system, no friction, back and forth continually, for forever. So we have the up and down, right? And then we can kind of show the different energies there. And then we can put a graph up here too, and we can kind of plot some of that, maybe with kind of just show this back and forth, right? So it's periodic, but it's constrained, right? In other words, you know, she can go, but she has to stay on this path, right? So that's what we call a constraint, right? And then I would just for those of you who have kids, you can actually build your own. So we'll do that, and then you can do something like this, and have her kind of jump off. Anyway, so you can build your own. But what I wanted to demonstrate is this periodic motion and just introduce this idea of a constraint here, right? So we've got a constraint. So let's look at some other examples of constraint, but let's bring this back out of sort of this playground and back into some real systems, things that you may see every day, or things that you're familiar with in terms of mechanical systems. Okay. So here's a couple examples of constraint. On the left-hand side, you have the cantilever beam. So what's the constraint on this? Well, the constraint here is that it's free to vibrate, but the one end has to be fixed and one end has to be free. Well, what ends up happening is you set up these modes of vibrations, like the first mode, the second mode, the third mode, right? You can see the modes of vibration and they can occur. So you can have periodic vibration on this beam, but it is constrained by being free and fixed. And then on the right hand side, we have a little bit different system where it has two opens, right? It's free on both sides, meaning that it has to come to a maximum when it hits the end for there to be a wave that sets up in there. And this is sort of like a pipe organ, right? And if you look at it, the length determines the wavelength. So the constraint here is that both have to be open, right? And you reach a maximum of vibration at the ends. And so you can see that if you change the length, you would change the wavelength, right? This first mode would be longer. You change the wavelength, you change the frequency. And so by changing these pipes, sizes, lengths, you can change the frequency, and that's how a pipe organ exists, right? You see a pipe organ, you see all those different pipes at different heights, right? And essentially what's happening is that you're changing, each one has a different length tuned to a different frequency. And so that's how we get them. So let's actually watch those in real life, in a real system. So, I couldn't get out of here without doing at least one motion amplification video. So here we have a system with a cantilever beam up there, and we're going to filter for the first mode of vibration. So that's like that cantilever beam that you saw, the first mode. And then here's the second mode. You can see that this is fixed, that's free. So we have the constraints. Here's the third bending mode, right? And here's the fourth bending mode. Now, I am going to go back. There's the fourth bending mode. I'm going to go back and look at this. You can see the bending mode. This would be the first, second, third. We don't see the fourth, but you can see these bends where it curves up. Okay, I'm going to play another video. Here is the fourth bending mode with vectors, and you can see that shape. That shape really exists in real life. That shape exists in real life too, and you can actually see that mode of vibration. Now, okay, so we've talked about vibrations and how they pop up in a mechanical system. We've solved that equation to show that they're periodic, and we talked a little bit about constraints on systems. So, we have these laws of vibration like periodic motion, but when they go into nature in real life, that's when we start getting constraints on things. So these rules, we have some rules that they have to obey. Okay, so now let's complicate things a little bit more. And I'm going to look at this system with a little bit different view, right? Let's think about, so far we've been looking at it in a 2D sense, okay? So let's think about it maybe in terms of 3D, waves in 3D, or a little bit more complicated. So this is water droplets. It's going to drop that in, and you can see these patterns come up. And this is called a wave front. These patterns going out, and if you look at the side, you can actually see, well, it's just periodic motion, right? Just periodic motion. But if you look at the top view, it looks very different, right? You can see these peaks and you can see the peaks and valleys represented by the shades, right? And again, the dark might be where there's a valley, and the blue might be where there's a peak, right? Okay. Okay, so you can do that. That's with water, but it's still similar. It's very similar in that it's a wave, just a different view of a wave. Okay, now I can look at sound, right? So let me turn on the sound, right? And you can see this is just a different way of representing the wave with a speaker, right? Doing the same thing. This is audio. Instead of the water, it's audio. Now, if I turned it on its side, what would we see? Well, surprise, surprise, it's exactly the same because this is three-dimensional. It's not just, you can't just look at it at its side. It's actually putting out a wave in three-dimensional space. It's symmetric all the way around. Okay. Now, let's bring this back to vibration. Okay. Let's bring this back to vibration. The vibration we know and love in with motors and pumps. Okay. So we're going to load this up, and this is a Fourier simulation where you can make waves. And we know that if you do the FFT, the fast Fourier transform, right, it allows you to turn a waveform into a spectrum, right? So I'm going to demonstrate that. And so we have a wave here. So each one of these bins represents a frequency, right? So think of this as a spectrum. 1 hertz, all the way at 2 hertz, 3 hertz, 4 hertz, maybe 5 hertz, right? It's more frequent, right? And there's the wave. But what we can do is we can actually go through and increase frequency 1 hertz, increase 2 hertz, increase 3 hertz, maybe skip 1 and increase 5 hertz. I'm just arbitrarily naming these 5 and 6 hertz. And you notice you've got all these different colors, right? And the colors represent the waveform for that individual. Watch, I'll highlight them. Green. The colors represent the waveform for the individual frequency. But we know that when we take data, on a machine, the vibration looks very different, right? It looks more like something messy like this, right? It doesn't look nice and clean like a single wave. That's because the waveform that we see when we collect data is the superposition of all these different waves at different frequencies. There's multiple waves summing together. If you sum all these waves together, you get this shape. And you can actually go through and look at what frequency content is needed to build a sawtooth wave or maybe a square wave. I think this one's kind of interesting. You can see it's not perfect square wave, right? But it's pretty close, and you can combine these diminishing, harmonics or the opposite intervals to build a square wave, right? So these real waves combine to form superposition of waves combined to form what is our reality, what is the real wave that we see, right? It's a bunch of combinations of different waves. So we've got this idea of constraints, and we've got this idea of superposition of waves that actually determine what a real physical system looks like, right? Based on just simple wave F equals ma and Hooke's law. That's really, the idea so far. Okay. So how does this all relate to quantum mechanics? Well, that's where Schrodinger's equation comes in. So there it is right there. I'm not going to solve that. But needless to say, Schrodinger's equation that you see right there with lots of different fancy symbols and, all represent something, right? But needless to say, for our purposes today, it's just a wave equation. And we can use it to actually make what they call a quantum harmonic oscillator. Very similar to a harmonic oscillator, like a spring that's moving back and forth, right? This is a harmonic oscillator for quantum mechanics, quantum harmonic oscillator, right? So it's a little unique. You know, it's not exactly an analog to the classic harmonic oscillator. It's a little unique because it has discrete solutions. Only certain states are allowed. Where did we hear that? We heard that back with the idea of the constraints, right? So the quantum harmonic oscillator is a little unique in that it only allows these certain states, right? These discrete solutions, right? And that's how quantum, like quantum is a packet. That's how it's not continuous. There's discrete solutions, unlike classical mechanics where, you know, you can allow lots of different positions in between. Quantum mechanics has these discrete solutions, right? And you can see them here, right? But where do we can see the different solutions to the waves. We can see these are the different states that are allowed, right? And energy states that are allowed. And where did we see this? Well, we saw this earlier. The idea that I wanted to show you here is with that constraint that we saw in the shape that we saw in the skate park, right? Where the girl was on sort of this curve. That was a constraint. She had to stay in this well. And this is what we also call sort of a well. It's a potential, sort of the potential energy states that can be allowed. Okay, so now let's look at that wave generator again. Right? So okay, so let's look at the waves again. Right? So we see the waves. Familiar with this? Turn it on its side. It's a normal set of waves, right? Okay. What happens when you have more than one wave? So we talked about that it's a superposition of waves, right? When you put two waves together, they superimpose on each other and they combine, add together, right? So let's do that. Let's do two, right? And you get the same pattern from each one, but they combine to make this very interesting pattern. So this is very similar to what we saw before. It's just with more than one wave. And what I wanted to really demonstrate here is this pattern, this idea of these dark and light areas where you have more intensity and less intensity, right? Okay, so now let's take that and let's apply it to quantum mechanics and look at wave interference patterns. So this happens to be the hydrogen wave function. So if you try to model the hydrogen atom, right, which is the most simple atom to do, right, you get these different states. And this is really talking about probability density for particles to exist in these locations, right? So that's what's really interesting about quantum mechanics. When you start to look at the waves, it actually starts where in one scenario where we talked about say the water or vibration, that's the intensity, and that's telling us how much vibration, how much motion there is, right? In this case, the waves are telling you what the probability of a particle existing there, say an electron, right? So in quantum mechanics, it turns out that when you look at an atom, the waves describe, there's not like you can say, okay, the particle exists right there, and you know over here you have another one. There's just a probability of it existing somewhere. It's most probable to be in the center, but there's some probability it could exist in this ring. And then for this state, there's high probability exists here, less probability that exists there. So that's what ends up happening when you start to solve these quantum mechanic problems with with these waves, these the superposition, right? And of waves, there's a probability that it's all about probabilities. There's a probability that electron exists somewhere, but you don't know where it exists until you measure it, which kind of gets a little weird, which we'll talk about in a second. And when you get into these systems, you know, in dealing with probability, one of the interesting things that I learned about, in statistical mechanics, like for example, you have all these molecules, just, in the room, right? You have all this air. There technically is a probability that exists that all of the air will be on one side of the room and no air will be on the other side of the room. In other words, all the air in the room will occupy half the room and it will be a vacuum on the other one. If you solve that problem, the probability of that happening is like way older than the age of the universe, or like the life of the universe. So like it's never going to happen, right? It's incredibly, incredibly rare, but there's still a probability of it happening. So weird things happen when you talk about probabilities, and one of which is Schrodinger's cat. So, okay, so we talk about this idea where particles are not necessarily there. There's just a probability of them being there because that's what the wave solution says, right? So here's Schrodinger's cat. This is a really famous kind of thought experiment where you have a cat, right? It's in a box. There's also a vial of gas or poisonous gas in the box, and you have this hammer attached to it that's going to hit the vial and break it and kill the cat if that happens, right? And that's attached to a meter, attached to a lever that you're measuring, right? And so the idea here, briefly, is that if you're using to find the probability of, say, a particle existing, when you're going to measure that particle coming out, and that determines whether or not the vial breaks or not, you don't know beforehand if the probability is going to be there that it's going to not break the hammer or it's going to break the hammer. And the idea is the cat, before you measure, the cat is both simultaneously alive and dead at the same time. And then when you measure it and you actually determine the location, right, then you know whether or not the hammer breaks the vial. So this caused a lot of, this was not a very popular idea at the time, or at least a lot of people had problems with it, because this idea of just chance or randomness in the universe with probabilities, was very new when quantum mechanics started to come into play. So anyway, that's Schrodinger's cat. It's the idea of just waves determining probabilities of particles existing at certain locations or not. Okay, so let's talk about where else waves show up, right? Where else do waves show up? Well, how about the Doppler effect, right? So we're real familiar with this. You have a car running towards you, and you can hear the pitch change as it comes towards you because the wavelengths shrink and the frequency gets higher. And then, of course, when it moves away from you, the frequency gets lower, right? And you hear higher pitched, and then as it goes by, then you start to hear lower pitch, right? And we all know this when an ambulance goes by or something like that. We hear that pitch change. So if we look at that sort of in multiple dimensions, kind of, in this pattern here, we can see this is just, say, something emitting a wave, right? Maybe that's a sound wave. And then we see it traveling forward, and we can see that, again, the Doppler effect, where the waves bunch up. And then we can see it when it breaks the sound barrier. In other words, the waves that are the sound that's being emitted in front of it, the object is actually caught up with them. It's traveling at the same speed, so therefore there's no sound in front of it. And then, of course, we have hyper or supersonic when it breaks the sound barrier. So here's another scenario where we've thought about waves, but now we're talking about how when you move, the wave kind of changes. The wavelength, the frequency changes. So we sort of threw a little kink in this idea of waves, right? Okay, so let's go back here, and I say, do you remember this, right? Remember this where we showed the waves, right? And if you notice down here, we have sound. We did this one. But if you notice, we've got a third one, light. Well, light behaves in waves, right? Light behaves in waves, but it's a little different, right? For this wave, the amplitude is how bright it is, but the frequency is the color of the wave. So if we change the color, if we change the frequency of the wave, we change the color of the wave, right? So that's pretty interesting and new. But we know Doppler effect changes, moving something to and from changes the frequency. So could we apply the idea of moving an object And would that change the way that light behaves? So what happens if we apply the idea of the Doppler effect, where if an object that's emitting a wave changes its frequency if it moves, dependent on whether you're behind or in front of it, right? What if we apply that same idea to light, right? Well, it turns out you discover the universe is expanding. That's essentially what happened when they applied that to light. So okay, so let's go back to our model. Let's see how that happens, right? Let's go back to our model and let's look at the light, right? Okay, so when we change the frequency, we're going to change. If we change to lower frequency, we're going to change to red. And if we're going to change to higher frequency, we're going to change to more blue or purple, right? So that means that if that applies, that means with the Doppler effect, if something is moving away from us, right? Something's moving, it should look more red. And if something is moving towards us, it should look more blue, right? Okay. Now, the problem is though, how do we know what color it was in the first place? How do we know what color it was in the first place? Well, it turns out that there is something called a type 1a supernova that when it happens, it is the same color every single time. It does not matter, where it is or, anything about it other than it's a type 1a supernova, same color. So now we have something they call a standard candle. Every time this supernova explodes, and it surprisingly happens a lot in around us, in different galaxies, that then we measure that, we know what color it should be, and we should be able to determine if it is more red or more blue. And it turns out we were able to do that. You can measure these supernovas and see some are red and some are more blue. And it turns out that they're able to determine essentially the Hubble constant, right? And determine that they looked around the galaxy and started mapping all these, and they found that all of this stuff is moving away from us. All of these things are moving away from us, and the further away it is, the more it's moving away. And what it turns out, a few steps further from that, they were able to discover the entire universe is expanding. It's not just the distance from these stars moving away, it's every point in space is moving away from it. So, I'm sitting here at my desk, the keyboard is moving away from me, and the microphone's moving away from me, my monitor's moving away from me. If you have somebody sitting next to you, they're moving away from you. The whole universe is expanding from all different locations. Okay, so that's interesting. And then we also were able to determine rotation of a galaxy. So if you look at a galaxy, one side, if it's rotating, one side would be moving away and one side would be moving towards you. And so you can apply the same idea of waves and just, extending it to the Doppler effect and show that one side looks more red and the other side looks more blue. That shouldn't be the case. They should be similar in color. They're made up of the same stuff. There's no special, something special about one side versus the other. So one is moving away from you, one is moving towards you, and we can show the galaxies are rotating that way. Okay, so how does this get us to gravity? So we've talked about quantum mechanics and we talked about light, but we talked about how gravity is also governed by waves, right? Okay, so let's talk about how do we look at this in terms of gravity? Okay, so let's look at these patterns of light that waves make. Okay, so if we do this experiment again, we look at the droplets, right? Okay, and now we go back to combining two, but we're going to look at it in terms of interference, right? We'll call this interference. The waves are interfering constructively or destructively with one another. It's another superposition. It's another way to coin it is interference, right? Okay, so there's another way you can do create these experiments with these patterns. You can put what they call a slit, right? And so you can do one slit where it's almost as if when you do this, kind of interesting, like it's as if it creates a new source of particles there, right? You can see that it's like this, each slit becomes its recreates a new source of particles. You can see the patterns coming out. And if I put two slits, you can see there's it's like two wave fronts coming out. It creates a new wave front. And you can see they're interfering with one another. You can see the superposition of waves there, right? And let's see here. So we have the graph, and then we can look at the pattern from that too. So let's turn this on, and we can look at a light source, and we can see these interference patterns. And this is called diffraction. We won't go into it. I just wanted to kind of point out the idea that these waves, the light waves, can interfere with one another as well, right? They can interfere with one another as well. They can constructively and destructively add to create these superposition of waves or this interference patterns that we see here. So again, they're kind of governed by the same principles where they add together and they subtract. And you can do it with mirrors. You can have two different sources, right? And you can have them take different path lengths. So we essentially, like if you think about it, what is determining whether these destructively or constructively add together? It's really their phase. It's really, are they in or out of phase with one another? And so by doing these experiments with different light sources, you can actually create these patterns where you get interference patterns where the light constructively or destructively interferes with one another. And these are some famous experiments where you kind of split these beams and you can actually change, you can constructively or deconstructively interfere, have the light interfere with one another, and you can actually separate the colors of the light, much like we separate the spectrum from a vibration into its spectrum. You can separate the light into its different spectrums of light with by constructively and destructively adding the waves together. But how do we apply this? How can we apply this idea of this phase, change that adds or subtracts waves together, makes them the intensity go up or go down? How can we apply it to gravity? Well, we actually do apply it to radio telescopes. So you can actually use multiple radio telescopes to look at light or coming in to be able to see, if they're in phase with one another. But let's go even bigger to gravity, right? Let's just go and talk about how we can use this idea of waves, right, to do something with gravity. Okay, so that's where we go to the LIGO experiment. So this is actually a very long pattern where they shot, light. They shoot light up and down these very long paths, right? So here's the idea. They shoot light up and down these paths, right? And when they get back to one another, they're exactly timed in phase. So the light pattern exactly lines up, and the signal gets bigger, right? Because we have constructive interference with the light, right? So what would cause these to deconstruct, or what would cause them to essentially the light to disappear? Well, if they were out of phase with one another. And one way we can do that is making one of these paths longer, right? Which essentially would require, if you kept this the same, if space-time, or essentially a gravity wave came through and distorted that and made one longer. And that's what they're trying to detect with these. And in 2016, they detected the first gravitational wave. It turns out gravity is just, and they had a theory that gravity was governed by waves, right? And so they set this experiment up, much like they would set up any experiment that they would do with light by exploiting the fact that light is governed by waves. they set it up for gravity to see if they could detect it, and they did detect it. So what is a gravitational wave? Well, it's essentially, so if you think of space-time, right? You think of like, the space-time is just like a blanket, right? And if you put something that has mass on it, it creates these wells that they set in, right? And that's what causes gravity. It's a warping of space-time by mass. And when you have something like two black holes collide with one another, it creates an event, just like we saw the waves in the water vibrate out, right? When these two black holes collide, it creates a ripple in space-time where you have a gravity wave that starts propagating out through the universe, right? And comes back to Earth and warps space-time so that one of these links is slightly longer than the other. And when that happens, then they destructively interfere and the light goes out. And that's what they're detecting. They're trying to detect the interference of the waves so that the signal disappears. And when they do that, they know they have a positive detection of gravity waves, and that's what they did in 2016. So to sum all this up, the idea is that waves govern everything from gravity to quantum mechanics to the motors and pumps that we monitor every day. So the next time that you see this, you can think of this, Schrodinger's cat, because it's essentially all the same concepts in terms of wave mechanics. So I'll stop here and we'll see if we have any questions. I'm happy to answer. And then also I just put out, there's my email address. If anybody wants to get in contact with me, I obviously enjoy talking about this stuff. There's our website, rditechnologies.com. And then we also have a YouTube channel because most of what we do is video, based. And so you can go to our YouTube page as well to be able to check out some of our content there. So we'll stop there and we'll see if anybody has any questions.
All right. I have 0 questions. I understood everything you said 100% clearly.
Awesome.
No, but all kidding aside, we do have a couple questions, and again, feel free to pop some more in here. We've got a little bit of time. Someone was wondering, it was a little bit towards the beginning, if the vectors are the vectors a new motion amplification feature?
Oh, okay. Probably this one. They've been around for a little while, so they're not new, but you can create. So we've had them for maybe a year and a half or so. So you can just add that if you in the motion amplification, you can kind of just draw vectors and put those on the screen to show the motion.
All right. Another one here. Does the amplitude of certain forcing frequency generated by motion amplification spectrum equal with the actual vibration measured by an accelerometer? I hope that makes sense.
Yeah, the answer is yes. Yes, those are calibrated measurements. So if those vectors are a representation of that, but they're related to, but the actual measurement that you would get out on a plot is equal to the amount that you would measure by acceleration. Now, keep in mind, if you go back to, kind of connecting that back to our talk today, both measure motion, but you look at this and you say this is acceleration, and acceleration, the A part here, acceleration is the rate of change, is the twice rate of change of a position. So an accelerometer measures acceleration while motion amplification measures displacement. You can connect those back to one another, which we do, but the answer is yes. They measure similar properties. They measure motion, but they come to the same. They come to agreement.
All right. Another one. How did they know it was gravitational waves?
Well, yeah, that's a good question, because it took them. Well, first of all, they had to get the experiment set up to be able to properly calibrate it. So so that involved a lot of sensitivity to be able to do, because the system had to be able to measure very, very small changes and very, very small vibrations. It's incredibly sensitive. The way that they know is ultimately they have an idea of what that should look like, what it takes to be able to change that. And so there's not very many things that can change that. So one, they have to rule out other things, right? They have to go around, they will have other controls within the experiment to be able to rule out other vibrations. Like for example, they might have like a seismograph or other things that can measure the vibration. So they can eliminate other sources to be able to deduce that it is a gravitational. So, and it's like any a gravitational wave. It's like any other thing. They have to build, they're essentially building a sensor that is designed to sense that.
All right, we'll do maybe one more here, and then, like I said, we'll share these questions with the RDI Technologies team, so they can hit you up with some answers offline. So let's see. Have you seen success teaching vibration or motion amplification to people without a STEM background?
Yeah, I think so, definitely. I mean, on some level, if you can, one thing I will say about those simulations, and I think that that's a good thing to bring up, these simulations that I showed, this is a real easy way. Like for example, this is kinetic energy, potential, thermal energy, but these mass and springs, it's a real easy way to be able to demonstrate vibration. So I think visualization, my personal opinion, and for me, and I think a lot of people really learn really well through visualization. If you can see it, it's a lot easier to understand. And so we have found that, like for example, motion amplification technology, where it makes it real easy to be able to understand vibration. Like for example, in this case, this is the vibration from the spring, the natural spring frequency. So to be able to show phase where one side goes up while another side goes down is very intuitive. So I think the visualization aspect makes it very handy to be able to teach vibration. We've had a lot of success with people understanding, taking maybe a vibration class, and then once they see these videos, they connect it. Or maybe they haven't taken a vibration class and they go straight into the videos and they understand, hey, I can understand what phase means because I can see these things aren't moving together.
Yeah, a couple people mentioned they really appreciated those visualization modules. So maybe what we'll do is share out the link to that on the Leading Reliability LinkedIn page as well, so folks can grab that if they didn't catch the link, because that was pretty cool. So. Okay, so Jeff, thanks so much. And I'm just going to take the screen back here as we wrap up, but that presentation that Jeff just did is a great example of the kinds of content that we will have at the actual in-person conference, in addition to a lot of actually bringing customers that are using motion amplification and their case studies and how they've had success. Same thing with, of course, the other host companies as well. Customers that have had great success with ultrasound, et cetera, et cetera. So a really cool mix of subject matter experts providing information on the different technologies and different principles of reliability and things like that, but then also real life use cases where you can kind of talk to someone and hear from someone who's gone through the ups and downs of implementing rather a technology or a new reliability program. So just another kind of plug for the conference. So if you want to learn more about that, it's the website is leadingreliability.com. Again, you can also find the Leading Reliability group on LinkedIn. If you have any questions, Jeff had his info up, but you can also reach out to us at UE Systems. We've got our email there. So we recorded this. We thank you all for attending today. We'll be back on Thursday with Skylar from Eruditio. And so if you haven't registered for that one yet, you can find the link again on our various LinkedIn pages. And with that, we'll let you all go and have a great rest of your day, and we'll catch you guys later.